This chapter is a very important one, and this term equilibrium you have studied in physics, but that is completely different from what we are going to do here. When you talk about physics, then equilibrium means you have a body, and that body, many forces are acting on it, but still there's no change in the state of rest or motion of the body. If it is in what is called rest, still many forces acting on it, it will still remain in rest, in a stable position. So that is static equilibrium. And if it is moving, again many forces are acting on it, but it is in a uniform motion, and then that remains in the uniform motion. So that is your dynamic equilibrium. So static and dynamic equilibrium you have studied in physics. Now the same thing we are going to utilize it in chemistry. So when I utilize this again here, we don't have forces, but we have to deal with reactions, isn't it? So when we talk about reactions, they are reactant, they are product, isn't it? So these things, they are converted from one to another. So how it is done, that we have to see how we can utilize equilibrium in this case. Okay, it's a very long chapter, but a very important chapter also. Very long and very important. When I take equilibrium, we'll talk about processes. Those process, some changes will be taking place. So what changes are going to take place, that we'll see, and then we'll talk about this equilibrium in details and its different types and other things. Clear? So very first thing, look here. When I take this equilibrium, then in this case, you'll see there are many changes. Some changes we write like this. Look here. If I take a piece of paper, if I burn this, what will be left? It's completely converted into something else, that is black colored substance, that is ash, isn't it? Paper, when you are burning it, it is converted into ash. This ash, can you get it back into paper? No, there's no way you can get it back into the paper, isn't it? So this type of things you have studied in lower classes. These are called, what do you call this type of process? This type of process, we call them irreversible process. Clear? But many times what happens when we are taking certain substances and we carry out a change, like if I take solid, if I heat it, it will melt into a liquid, and this, if I again cool it, then it goes back into the solid state, isn't it? So here what is happening, the process is possible in both the directions, isn't it? The solid can be converted into liquid, the liquid can also be converted back into solid. What you have to do, the conditions are different, so these are reversible. Reversible process. Now this reversible process is needed for equilibrium. So if the process is irreversible, we don't have equilibrium in it. Okay, and irreversible process never attains equilibrium. If it is a reversible process, then it can. Okay, but irreversible process never attains equilibrium. That is one of your things which you have to know. Clear? So we have to talk about reversible process, isn't it? A reversible process. A reversible process can attain equilibrium. Now, it does not mean that all reversible processes will attain equilibrium. Clear? So when I take this reversible process, there are two processes taking place. One I can term it as forward, another one I can term it as backward, isn't it? So the forward process and the backward process, if they take place at the same time, it's not that forward can take place under one condition and backward can take place under another condition. It's not like that. They have to take place at the same time. Okay, a reversible process can attain equilibrium if both the forward and backward process occurs simultaneously. So the forward process and the backward process, both of them, they have to occur simultaneously, means at the same time. Okay, and when it is taking place at the same time, then one more thing will come in here. When the changes are taking place, then the changes should take place at the same rate. The rate at which the forward reaction is taking place, then that should be same as the rate at which the backward reaction is taking place. Clear? So if both the forward reaction and backward reaction or the process occurs simultaneously at the same rate, and backward process, the forward and backward process are taking place at the same rate at the same time, then only equilibrium can be established. So what will happen when this change is actually taking place? The forward reaction or the forward process and the backward process, if they occur at the same rate, basically you won't see any change in the concentrations. Whatever was the concentration before and whatever is the concentration now, that will be exactly same. So it seems that there's no process taking place actually. Okay, but both the processes will be taking place in full swing. It appears that nothing is happening. Okay, so this state. That state we'll call it equilibrium. Is it clear? Okay, then next thing, if I take it like this way, look here. We'll talk about the reactions and all those things one by one. But first, let's talk about this changes which can occur there. Okay, suppose I take ice and melt it. Then if I take 10 grams of ice, it will start melting, isn't it? So initially what will happen? Only the ice will melt. But if the temperature is kept the same 0 degree, then freezing of water can also take place. So what will happen? Slowly water will start freezing also. So both the ways the process will take place. Suppose 10 grams I have started with, isn't it? Slowly it becomes 9, 8, 7. But at the same time, the amount of water which was increasing, that will also start freezing. So what will happen? The amount, suppose when it reaches 6 grams of ice, then 4 grams of water was there. At that time, maybe the rate of forward process, means melting, and the rate of backward process, that is freezing, may become equal. So if it becomes equal, what will happen? You'll see there's no change in the amount. 6 grams of ice will remain 6 grams of ice. Clear? And 4 grams of water will remain 4 grams of water. There's no change. So the concentration does not change. Okay? So that state, although it seems that nothing is happening, but the change is actually taking place. So that state we call it equilibrium state. So equilibrium state. If I take this, then what is it? Equilibrium state is the state at which the rate of forward process is equal to the rate of backward process. So rate of forward process and the rate of backward process will be equal, is the state at which the rate of forward process is equal to the rate of backward process. So apparently what will you see? Forward and backward is taking place at the same rate, isn't it? Therefore, there is no change in the concentration of any component. Whatever is the amount, that will remain the same. There's no change in the concentration of any component and other physical conditions. Other physical conditions also remains same. Whatever is the temperature, it will remain the same. Whatever is the pressure, that will also remain the same. So apparently no change is observed. So what I can say here is, apparently it seems that no change is taking place. But actually both the process are taking place in full swing. That means they are taking place at the full pace. It looks like there's no change because there's no change in temperature, no change in pressure, no change in concentration. But the forward and backward reaction are taking place at the same rate only. So apparently you don't see anything. Is it clear? So basically the changes will continue, but apparently nothing can be seen. Observation, nothing will be there, but practically everything is happening. Then the next thing, when I take this, since both the processes are taking place in full swing, it is also called dynamic equilibrium, because it is actually the reactions are taking place or the process is taking place. Hence, it is also called dynamic equilibrium. Yeah. So we'll take some examples and then we'll see what other things can happen. So let's take some. I'll give you different types of examples and then we'll classify the equilibrium also. I can take the first example like this. Ice can melt into water and water can go back into ice. Isn't it? This occurs at a particular temperature. We'll talk about that, but this is just the changes which can take place. So this can come into equilibrium. Okay. Another example I could have given you is like this. Look here. If I take this reaction, you have done this reaction, nitrogen can combine with hydrogen. And when nitrogen and hydrogen combines, it forms ammonia. This is a very important process, that is Haber's process. Isn't it? This Haber's process, the reaction is reversible. Remember, if it is reversible, then only there's chance of equilibrium. So the first one also, you can see this sign, that is reversibility is there. In the second one also reversibility is there, isn't it? So this can be reversed back, isn't it? Nitrogen and hydrogen, they combine to form ammonia. At the same time, ammonia can also decompose into nitrogen and hydrogen. Clear? So that is there. So this also can take place. Apart from this, another thing which we have studied, suppose I take ionic salt. An ionic salt can be, suppose I take calcium chloride and dissolve it in water. CaCl2. I can add it to water. You know, when an ionic compound is added to water, this will break up into the ions. 2Cl minus, isn't it? They break up into ions. You have just added water, it dissolves, and then when it dissolves, it dissociates. So this process is also reversible, because if you what is called evaporate the water, it will give you a solid only, isn't it? So what is happening? This is also, it can attain equilibrium. The rate at which they are dissociating and the rate at which they are combining should be equal, isn't it? So in this case, what happens? Equilibrium can be established. So three cases I have given you in which you can establish equilibrium. Okay, it's not that I'll just write down this and it is in equilibrium. There are certain conditions under which equilibrium will be established. We'll go into details of all those. Clear? But basically, here what you can see is the first case. Ice is converted into water and water is converted back into ice. This is just a physical change, and therefore this will refer to it as physical equilibrium. So whenever the equilibrium is established between some changes where only physical change is taking place, then we'll term it as physical equilibrium. But if I take the second one, in that case a chemical reaction is taking place, and that also can attain equilibrium. So here I'll call it chemical equilibrium. In the second case, it is chemical equilibrium. And when I take the third one, there also a change is taking place. You cannot term it as a reaction. It's just dissociation into ions. Clear? CaCl2, I can make it a saturated solution. Then this will be a solid. This will be in solutions, isn't it? So if this type of things are established where ions are also involved, then in that case we'll call it ionic equilibrium. So three different types of equilibrium you can see: physical equilibrium, chemical equilibrium, and ionic equilibrium. That means your chapter can be divided into three parts, and each one is individually different from the other. These three are completely different from each other. They take place under different conditions and all those things, but basically one thing is common in all: the process has to be reversible. That means reversibility has to be maintained. And the second thing which we talk about is the rate at which the forward and backward process has to take place. Clear? So the first thing, reversibility. Reversibility has to be maintained. And the second thing, rate of forward process should be equal to rate of backward process. So forward and backward process, the rate has to be equal. So these two things are maintained, means only if it is reversible then the second one can happen, isn't it? So if this is maintained, then the process comes into equilibrium. Is it clear? So one by one, we'll see each one of this type of equilibrium. So there are three types of equilibrium you have already seen, isn't it? So the first type we'll talk about is your physical equilibrium. So just now I told you physical equilibrium. When is it established? When the physical properties are involved, isn't it? It's just a physical change. Then that equilibrium will term it as physical equilibrium. Okay. So you want to write down the definition. Then physical equilibrium is the one which is established, means the equilibrium is established, you are involving physical process. Only the physical properties they change, isn't it? There is a interchange in the physical properties. Only the physical properties they change. Okay, so since we talk about physical changes, the changes which we will be studying, that will be solid can be converted into liquid. So this can establish equilibrium. We can have liquid can be converted into a gas, and solid can also be converted into gas directly without going into liquid. Yeah. So these three types of equilibrium, let's see one by one again. These all are physical, only physical changes are taking place. The change of state is involved, isn't it? Chemically, the substance remains the same. Okay, so this you will have copied, isn't it? So we'll start with one by one. The first one we'll see is solid liquid equilibrium. Solid liquid equilibrium. Here, when I talk about this, the most common example when a solid is converted into a liquid that I can give you is uh, ice is converted into water. So when ice is converted into water, we don't see any chemical change. This one, ice is H2O only, and water is also H2O. So chemically they are same. So this is a physical equilibrium. But for this to be established, when can it be established? Ice is converted into water, and water is also converted into ice. This process has to take place at the same time, isn't it? So this process you cannot carry out at any other temperature except the melting point of ice. What is the melting point of ice? You should be knowing. Anyone? Melting point of ice is same as freezing point of water. So what is it? This can take place. This process can take place only at 0 degrees Celsius. That means if the temperature is 1 degree, ice will not be there, only water will be left. That means it cannot this equilibrium cannot be established. If I go to minus 1 degree, only ice will be left, water will not be there. So at 0 degrees Celsius, this equilibrium can be established, isn't it? So there is a condition. It cannot occur at under all conditions. This can take place only at this condition, isn't it? That means uh, this this process can attain equilibrium only at the melting point of the solid, actually, isn't it? And melting point of the solid actually is the freezing point of the liquid. Okay, that means the one which we are talking about is 0 degree Celsius, or if I take in Kelvin scale, it will be 273 Kelvin, isn't it? If I go any uh, temperature change, then this equilibrium is lost. Okay, so melting point of the solid, and again the pressure plays a very important role at normal pressure, because if the pressure changes, the melting point also changes. Clear? So here what will happen when you are studying this, then in this case basically both the process will take place. That means uh, ice will melt and it will form water. At the same time, whatever water is present there, that will freeze and form ice. That means whatever ice has melted, the same amount of water will freeze, isn't it? Because the rate is same, and therefore the amount of ice will also not change, the amount of water will also not change, isn't it? So in this process, what I can write down here is the forward process. If I take, that is the rate of melting of ice will be equals to the rate of freezing of water. If these two processes are equal, then you'll say the equilibrium is established, isn't it? And this to be established, there's the condition. What is the condition? Only at its melting point it can be established. Any other temperature, it cannot be established. So for solid liquid equilibrium, condition is there. The main condition, this can take place only at the melting point. Clear? And if this thing is established, rate of forward reaction and the rate of backward reaction are having equal rate, then what I can say, the system is in dynamic equilibrium. The system here is in dynamic equilibrium. Why we are saying this? Because both the opposing forces, remember melting and freezing, they are opposing, isn't it? So what I can say, both the opposing forces, both the opposing forces occurs, or not forces, you just add on process, then it is better word. Both the opposing process occurs simultaneously. That's what we have seen, isn't it? The second thing, both the process both the opposing process occurs at the same rate. And the third thing I can say here is the amount of ice and water. You have already taken ice and water, isn't it? The amount of ice, whatever was there, and whatever water we have taken remains constant. Means there's no change. Whatever we take, then slowly the equilibrium will be established. Once the equilibrium is established, the amount does not change. Okay, then we'll continue. We go to the second type of equilibrium now. Not second type of equilibrium, it's physical equilibrium, the second type. What is it? The second one which we have to know is liquid vapor or liquid gas equilibrium, we can say. Liquid vapor equilibrium, or you can also call it liquid gas equilibrium. Now, here also, when this takes place, what will happen? We are talking about liquid changing into vapor. That means again change of state. isn't it? And this change of state, we call it vaporization or evaporation, also you can call it, isn't it? So here what happens, look here, I could have taken water vapor is being formed from water, isn't it? So liquid is now converted into vapor. Now for this liquid to be converted into vapor, we are mainly considering the process of evaporation. Liquid to vapor means evaporation. We are not talking about boiling, because boiling, what will happen? That takes place at a higher temperature, isn't it? And it is a rapid thing. Here, what will happen? Evaporation, when it takes place, when we are considering evaporation, then it can occur at any temperature. So here there is no restriction of temperature. Equilibrium occurs at all temperature. So when I take this, then in this case, what is happening? Look here. If I take uh, liquid in a container, suppose I have taken this container, I have taken a certain amount of liquid. Yeah. If I just leave it open and measure the same thing in the next day, will the amount of liquid be same? No, it won't be same. What will happen? The amount will be less, because what will happen, from this certain liquid they will evaporate. So usually what happens, the rate of evaporation for different liquids are different. Some they evaporate faster, like suppose I take petrol, alcohol and all those things. If I keep that liquid and next day if I see open, if I leave it open and then see it on the next day, then I won't find anything, because everything will evaporate. Nothing will be left there. But if I take other liquids like oil, water, and other things, they are less volatile than comparatively, isn't it? So what will happen? That will be left, but the amount will be less, isn't it? There are many things which are non-volatile only. There are many oils and other things which do not go into vapor state directly, but they take a very very long time. So things can be volatile, may not be volatile. But if liquid is converted into vapor, evaporation has to take place. So this has to evaporate. Now, when liquid evaporates, the vapors they go into the gas, they mix up, and therefore you don't observe any change, isn't it? But basically, what we have to do here is to establish this equilibrium, the vapor and the liquid both has to be together. So if I leave it in open, it will never come into equilibrium, because the gases they diffuse into the atmosphere, they are lost. So we have to what is called, keep it there only. The vapors have to be confined. Then only this can be, the equilibrium can be established. So that's why what we will do, we'll take this and we'll put it in a closed container. Suppose the container is closed. I can close the container. Okay. So if the container is closed, what will happen? The liquid will evaporate, vapors will be formed, and these vapors and the liquid are together now, isn't it? What will happen? Slowly the liquid evaporates, the vapors are formed. If I connect this to a manometer, the manometer will measure the pressure, isn't it? You can just connect this to manometer. So this manometer is measuring the pressure. What will you see? When I just close it, initially what will happen? The pressure inside and the pressure outside are exactly same. It is the atmospheric pressure. But if I leave it closed, and observe the manometer, then what will you see? Slowly there is a increase in pressure inside the container. The container is confined, so nothing can come out from there, isn't it? So a slow increase in pressure is observed. Why? Due to the accumulation of vapor in the container. So whatever container is there, slowly these vapors are being accumulated. So the pressure inside will slowly go on increasing. Understood? Now, what will happen? You could see the pressure increasing, 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 isn't it? And suddenly it will reach to a certain state and then it remains constant. Clear? A steady increase you can see in the beginning, isn't it? Then, after some time, the pressure becomes constant. Slowly it was increasing, 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 isn't it? Then what will happen? After some time, it was increasing, increasing. After some time, it comes to a constant. Then beyond that, you don't see any increase in temperature. There was an increase, it was going on increasing, but after some time, the increase has stopped. Why it has stopped? That you have to know first. Then I'll tell you other things. When these vapors are coming in here, the vapors are accumulating, but this space is limited, isn't it? So what will happen? Think that the entire space is filled up now. If the entire space is filled up, what will happen? Will the process of evaporation stop because there's no place for the vapors to go? Will the process of evaporation stop? No, it won't stop. Okay, the process of evaporation will not stop. But what will happen when the evaporation is taking place? Suppose two particles evaporate, then two particles will condense also. That means evaporation and condensation are taking place together at the same rate. So that's why there's no change in pressure. Whatever evaporates, the same thing condenses. So the number of particles in the vapor state are not changing, and therefore the pressure remains constant. Is it clear? So now, if you see inside the container, the liquid is evaporating also and it is condensing also, isn't it? So evaporation and condensation both are taking place. That means at the same rate. So what you can say? Equilibrium has been established because rate of evaporation and rate of condensation has now become equal. Understood? So now look here. What you have to know here is this. If I had taken this one, then in this case, uh, just now I told you the pressure increases. There's a steady increase, and then after some time it becomes constant, isn't it? So it becomes constant means the inside pressure is more. So what can you say? Suppose the outside pressure is 760 mm. That is your normal atmospheric pressure. The pressure inside will be more than this 760. So suppose the pressure inside is 800. I'm just taking an example. Then what will happen? How much extra is there? 40. Isn't it? 800 inside means the pressure inside is 40, and that 40, the extra pressure inside, will be how much? 40 mm. And this 40 mm is due to what? The vapors, because the atmospheric pressure is 760. The extra pressure is because of accumulation of the vapors. So this 40, the extra pressure here which we are getting, this pressure we'll call it vapor pressure of a liquid. Okay, this extra pressure is called this pressure, this extra pressure you can say. This extra pressure is called vapor pressure of a liquid. Is it clear? So if suppose I ask you what is vapor pressure of a liquid, then what will you say? What will it be? It is the pressure exerted by the vapors only. But when the liquid is confined and the liquid and vapors are in equilibrium. If they are not in equilibrium, then that is not vapor pressure. So first they have to come into equilibrium, and then whatever extra pressure is there, that extra pressure we'll call it vapor pressure. Okay. So what you can say, vapor pressure is the pressure exerted by the vapors, exerted by the vapors in equilibrium with liquid. In equilibrium with the liquid in a closed container. The container has to be closed at a given temperature. If the temperature changes, then the rate of evaporation will change. So that's why the vapor pressure might change. Okay. So here, this is vapor pressure. Now this vapor pressure is attained, then only equilibrium can be there. Suppose I take a liquid and vapor, and this vapor pressure is not yet attained. That means the system is not in equilibrium. That means the condition here is for the liquid vapor equilibrium. The vapor pressure has to be attained. In the container, you should get the vapor pressure. It takes place at the vapor pressure of the liquid. In the previous case which you studied, in that case, what was that? It was taking place only at its melting point. So there was a condition there. Here, this can take place only at the vapor pressure of the liquid. That means the pressure has to be the vapor pressure. Then only this will take place. Clear? So the condition is there in physical equilibrium. The process governed, always the process is governed by certain uh, parameters. In the first case, it was melting point. Here it is vapor pressure. So this takes place uh, at the at the vapor pressure of the liquid. This takes place at the vapor pressure of the liquid. Otherwise, this equilibrium will not be established. So, in this case, what I can see is, okay, for liquid vapor equilibrium, what I can say, rate of evaporation should be equals to the rate of condensation. So rate of evaporation of the liquid should be equals to rate of condensation of the vapor. So this is established, then only equilibrium is there, isn't it? And this condition, when is it established? This condition is established when the liquid attains its vapor pressure. Isn't it? This equilibrium is established when the liquid attains the vapor pressure. Vapor pressure of a liquid is constant. Okay, so if it is at its vapor pressure, then at that vapor pressure, this equilibrium can be established. Okay, and look here. This vapor pressure becomes equal to the atmospheric pressure. Then the liquid starts boiling also. So at that point, what will happen? The equilibrium can be established. When the vapor pressure becomes equal to the atmospheric pressure, then the liquid starts boiling. So this boiling also, it can attain equilibrium, but this is at a higher temperature. Liquid starts boiling and the temperature at which this becomes equal or this happens is called boiling point. That means if you don't want to establish equilibrium at room temperature or any other temperature, then it can always be established at its boiling point. The boiling point, the liquid is going into vapor, the vapor is condensing, that can happen. That means water and steam can be in equilibrium at its boiling point. If this condition is taken, then you know it is 100 degrees Celsius. Boiling point of water is 100 degrees Celsius or 373 Kelvin. And the pressure has to be 1 atmosphere or 101.3 bar. So under this condition, equilibrium can be established between water and steam. So there are two things. Either it can be established at the boiling point, which is generally higher, or it can be established when the vapor pressure is attained at any other temperature. It has to be a confined liquid. You all must have observed your water bottle and all those things. Suppose half filled, sometimes half filled water bottles, when the cap is closed and you leave it overnight, you'll see lots of droplets of water deposited on the empty part of the container of the bottle, isn't it? So that is due to condensation. So rate of evaporation, that means inside the equilibrium has already been established. Okay, so today's class will do this much only. Revise all these things. Next day we'll continue from here. Any problem up till now? You'll let me know. Any problem? Anyone? No. So today's class will end up here only. Okay. Thank you, all of you.